All right, here we're going to look at just a couple of examples applying the formulas, the integral formulas, identities for hyperbolic functions, right? So first let's start with something like this. The hyperbolic sine of root x over root x dx. Okay. Now I do know what the integral of a hyperbolic sine is, right? But here I have a bit of a difference, not a straightforward type function. Okay, so what we have here is I need to do a substitution. All right, now how do I know I can do a substitution? It's really the root and the derivative of the root being 1 over 2 square root of x, which I see on the outside, right? Not necessarily the 1/2, but that's okay. I can always multiply in a factor. Right, so once kind of I've identified that, I want to say, all right, let u equal to the square root of x. Right, and then du is equal to 1 over 2 root x times dx. Right, now I see the dx over root x out here. I don't see the 1/2, so multiply both sides by 2, and we get dx over root x. All right, and now I'm able to substitute. Right, here we have the integral of the hyperbolic sine of u, and then root x, dx over root x is replaced by 2 du. Right, and now here we go, right? That simple substitution here allows me to now have a straightforward integral. We have cosh of u, don't forget the plus c, and then also here changing back to my x variable plus c. All right, and that's how we apply the formulas for the integral, right? Let's do one more. So now here, we'll do the integral cosh of x over cosh squared x minus 1 dx. All right, so when I see this right away, I think, all right, there is some kind of a trig identity for the cosine, or hyperbolic identity for the cosine, or the hyperbolic cos. In particular, the squared, right? I look at the denominator, I'm like, oh, this looks like I can apply that hyperbolic cosh, hyperbolic there, right? The one that relates cosh squared of x and sinh squared of x. So that's related in this form, right? A little different than the Pythagorean, right? It's not based off the circle. Is actually based more off the hyperbola, hence the name hyperbolic function. Okay, so now in that case here, it looks like the cosh squared of x minus 1 is equal to sinh squared, right? Just by basic kind of algebra here, maneuvering, moving things around. Okay, and then from here, so substituting that in, we get cosh of x over sinh squared of x dx. Right, and again, why I wanted to do that is I have a relationship between the sinh and the cosh, right? Their derivatives are equal. They're related by their derivatives, all right? So I know I want to, looking at this, I see, well, I can now use the power rule, right? Even though maybe it's not obvious here, right? But when you start thinking, all right, what is the substitution here? If the substitution is this, right, just the sinh, right? So I'll have u squared at the bottom, right? Du is cosh x dx, which is exactly what I have here, right? And that's why I chose the substitution the way I did. That's why I did the initial identity using it to change it to cosh squared, right? Because now it allows me to come here and say, all right, well, this is du over u squared, right? The idea is that the integral now becomes more straightforward, right? If you do a substitution and the integral it becomes more complicated, then there was probably something wrong with that substitution, right? And the goal of the substitution is to simplify the integral, right? And here this becomes negative u 1 over negative u, right, or u to the negative 1 plus c, and then back substituting, we get 1 over sinh of x plus c. All right. And that's how we can use some basic integrating techniques with the hyperbolic cosine and the sine.